Hello, my dear physicists. How are you all? Since Nobel Prize week is going on, we will be talking about the work of the physicists who got Nobel Prize in Physics in the last 5 years. This year's winner have also been announced, and I will be making a video on them soon, so stay tuned for that. Nobel Prize is just an excuse for us to talk about a little more physics. 2017. It was awarded to Rainer Weiss, Barry C. Barish, and Kip Thorne for decisive contributions to the LIGO detector and the observation of gravitational waves. Gravitational waves were predicted by Albert Einstein almost 100 years ago by his theory of general relativity, and the waves that LIGO detected came from the collision of two black holes 1.3 billion light years away. Just think about it. These waves traveled for 1.3 billion light years across several galaxies and planets just to be detected by us. 1.3 billion years was even before multicellular life evolved on Earth. Isn't that amazing? Gravitational waves are disturbances or ripples in space-time generated by accelerated mass, and they propagate as waves outward from their source. Just like when you move in water, there are water waves produced. In the same way, when a mass moves through space-time, gravitational waves are produced. Just like when you move through water, you lose some energy and slow down. In the same way, when a mass moves through space-time, it loses energy to these waves and slows down. You produce gravitational waves too when you move your hand through space-time, but they are too weak to be detected. But when a massive object like a black hole moves through space-time at incredible speeds, it produces gravitational waves strong enough to be detected here on Earth by our gravitational wave detectors like LIGO. The first direct evidence of their existence came in 1974 from the observed orbital decay of the Hulse-Taylor binary pulsar. When these two binary stars revolved around their common center, it was observed that they were coming closer together as they lost energy. And the reason for their loss of this energy was that their energies were carried away as gravitational waves they produced, and the decay rate was as predicted by Einstein's general theory of relativity. The direct evidence of gravitational waves did not come until 2015, when it was directly observed by LIGO. 2018 Nobel Prize in Physics. The 2018 Nobel Prize in Physics was awarded to Arthur Ashkin, Gerard Mourou, and Donna Strickland for groundbreaking inventions in the field of laser physics. One half of the prize went to Arthur Ashkin for the optical tweezers and their applications to biological systems, and other half jointly to Gerard Mourou and Donna Strickland for their method of generating high-intensity ultra-short optical pulses. Let us start with optical tweezers. You must have heard about the Einstein's famous equation E equals to mc square. Now, the mass of light is 0, so plugging in m equal to 0, energy of the light comes out to be 0, right? Actually no, the full equation is not E equals to mc square, but E square equals to p square c square plus m square c raised to the power 4. If an object is stationary, meaning it has no momentum, then the equation reduces to E equals to mc square. But if the object has no mass, like in the case of light, then the equation changes to E equals to pc, where p is the momentum. Now we all know that light has energy. That is why we can feel the warmth of the sun due to the heat energy given off by the light. So by this equation, light also has momentum, which is equal to E by c. Keeping that in mind, let us look at this setup. This is a lens that bends light. If we shine the light on the right side of the lens, the light bends to the left. Initially, there was zero momentum in the horizontal direction, but now the light is slightly going in the horizontal direction, which means there is some momentum in the horizontal direction, specifically in the left. By the law of conservation of momentum, the momentum in the horizontal direction should be conserved, which means the lens acquires a momentum in the right direction to cancel the momentum of light in the left, and hence the lens starts to move right. In the same way, if we shine light in the left direction, the lens also moves to left. Now replace the lens with a spherical glass ball and replace the light with a laser light. We will choose a laser which has high energy in the center, and the energy decreases as we go away farther from the center. When we shine the light on the sphere, the left side of the laser tries to move the sphere to the left and the right side to the right. Due to this, the sphere moves nowhere as the forces cancel out each other. But if we put the sphere a little off center, the part of the light beam with higher intensity goes up and the part with the lower intensity goes down. So there is a greater force in the downward direction due to the high intensity beam and less force in the upward direction. Hence, the ball moves downward from the center of the beam. In the same way, if the sphere is kept a little off center in the downward direction, the ball moves up towards the center of the beam. This means that the sphere is trapped in the beam. Even if it goes a little off center, it moves back to the center just like a ball stuck in a valley. The ball always rolls down if it moves a little here and there. This is the principle behind optical tweezers. Using light to capture extremely small objects, we can attach different molecules on the sphere to study their tensile strength, their spring constants, etc. The other half of the prize, which was given to Donna Strickland and Morrow, was for their method of generating high intensity ultra short optical pulses. In simple terms, they were awarded the prize to invent a way to create incredibly powerful lasers. Lasers so powerful that when they are fired, they have more energy than a million nuclear power plants for a fraction of a second. A laser light is produced by a process called stimulated emission. When a light of a single wavelength passes through a medium inside a laser, the excited atoms of the medium lose their energy and create the same wavelength of light. This process can be repeated multiple times to increase the power of the laser and then release all of it in a short burst. But nowadays, the lasers have become so powerful that they would melt the mirror that is used to reflect them. So, to tackle this problem, Donna Strickland and Morrow created a technique called chirped pulse amplification. What this technique does is it takes a beam that is powerful and stretches it in time, which means reducing the energy density of the laser. Then they amplify the signal to just below the threshold power that would destroy the components. And then they compress the laser back to its original energy density. This way, they don't destroy the components and create a ridiculously powerful laser. Simon Clark created a brilliant and detailed video on this. You can watch his video after you watch mine. Link in the description. 2019 Nobel Prize in Physics. This prize was awarded to James Peebles, Michael Mayer, and Didier Queloz for their contribution to our understanding of the evolution of universe and Earth's place in the cosmos, with one half of the prize given to James Peebles for theoretical discoveries in physical cosmology and other half jointly to Michael Mayer and Didier Queloz for the discovery of an exoplanet orbiting a solar-type star. James Peebles did many important contributions to the Big Bang model. He also predicted the cosmic microwave background radiation, or CMBR, which is a faint glow in the microwave part of electromagnetic spectrum which comes after universe just became transparent, which was only 400,000 years after the Big Bang, which means CMBR is the oldest light which we can see, and by using it we can study the birth of the universe. Michael Mayer and Theodore Queloz discovered the first exoplanet orbiting a sun-like star in Milky Way in 1995. This discovery started a revolution in astronomy, and over 4,000 exoplanets have since been found in the Milky Way. Several new planets are being discovered by scientists, challenging our understanding of planetary formation. With numerous projects planned to start searching for exoplanets, we might eventually find an answer to the eternal question of whether other life is out there or not. 2020 Nobel Prize in Physics. 2020 Nobel Prize in Physics was awarded to Roger Penrose, Andrea Ghez, and Reinhard Genzel. Roger Penrose got the prize for the discovery that black hole formation is a robust prediction of general theory of relativity, and the other two got the prize for the discovery of supermassive compact objects at the center of our galaxy. Roger Penrose used mathematics to describe black holes and showed that while general relativity means the formation of black holes must be seen as a natural process in the development of the universe. Reinhard Genzel and Andrea Ghez each led a group of astronomers since 1990s and focused on a region at the center of our galaxy known as Sagittarius A star. They found that something extremely massive, around 4 million solar masses, was packed in a size of less than that of our solar system and was causing the stars in the surrounding to move at astounding speeds. They used Earth's most powerful telescopes to see through huge clouds of interstellar gases and developed techniques to account for the distortion caused by Earth's atmosphere in their data. They provided concrete evidence that there is a supermassive black hole lurking at the center of our galaxy. Of course, we got the image of the black hole recently using the Event Horizon telescope, which confirms that there indeed is a supermassive black hole at the center, just as the two Nobel Prize winners predicted. 2021 Nobel Prize in Physics. The 2021 Nobel Prize in Physics was awarded for groundbreaking contributions to our understanding of complex systems, with one half jointly to Syukuro Manabe and Klaus Hasselmann for the physical modeling of Earth's climate, quantifying variability and reliably predicting global warming, and the other half to Giorgio Parisi for the discovery of the interplay of disorder and fluctuations in the physical systems from atomic to planetary scales. So what are complex systems in physics? You guys must have heard of butterfly effect, right? That flapping of butterfly wings in one part of the world can cause massive tornado in other parts. So what this sentence is actually trying to convey is that in some systems, a small change in one part can cause a massive change in other parts further down the line, like the double pendulum. A single pendulum's motion is very easy to predict, just a simple to and fro motion. But add one more pendulum in the bottom of the first, and you got yourself a complex system, which is extremely hard to predict, borderline impossible, because a slight variation in the starting position of the pendulum would lead to extremely different trajectories. This is an example of complex system, systems whose behavior is seemingly impossible to predict. Weather is also a complex system. This is the reason that weather forecasts of more than 1 week ahead are almost random guesses. Earth's climate is also a complex system. Shikuro Manabe showed that increasing carbon dioxide levels in the atmosphere causes rise in Earth's temperature and laid the foundation for current climate models in 1960s. Then 10 years later, Klaus Hasselmann created a model that links together weather and climate, thus answering a question of why climate models can be reliable despite weather being changeable and chaotic. He also showed that climate change is happening due to human emissions of carbon dioxide. Around 1980, Giorgio Parisi discovered hidden patterns in disordered complex materials. His discoveries are among the most important contributions to the theory of complex systems. They make it possible to understand and describe many different, apparently random phenomena. This is not only useful for physics, but also in other very different areas such as mathematics, biology, neuroscience, and machine learning.
If you guys liked the video, which I am very sure you did, then consider subscribing because more exciting content is coming soon. Until next time, remember, be curious and keep learning.